Picture a square with 4 sides laid out in 2 dimensions. Now take the corners and extend lines going perpendicular to the square, piercing into the 3rd dimension and forming a cube. Now take each of the 8 corners and extend a new line from each of them, this time piercing into the 4th dimension, perpendicular to every existing line in the cube. This is a hypercube, also known as a tesseract. Higher dimensional objects are almost impossible to envision in your mind's eye, but if you can, scientists in mid-19th century England believed great rewards would come your way. For many Victorians of the time, the 4th dimension represented the realm of the spiritual, the font of divinity. It had started in science, with mathematicians like Bernhard Riemann, who had just devised a new kind of extra-dimensional geometry beyond the triangles of 180 degrees and parallel lines we had known before. And from there, the fertile Victorian imagination turned the 4th dimension into an almost magical realm, where we could find commune and connection. But for H.P. Lovecraft, a New England author born towards the end of the century, within the higher dimensions of the universe, he found only horror. In one of his tales, The Dreams in the Witch House, Walter Gilman, a student of physics and mathematics, finds that the room he is renting has bizarre dimensions. Dreams come to him every night, drawing him deeper into higher dimensional planes filled with gods and monsters. This Lovecraftian fear is fundamental and inescapable. It is a fear of the unknown, a fear of the true scale of the wide universe and what lays beyond. And yet, some of us are brave, or at least foolish. Some scientists have peered into the depths of the cosmos, seeking the darkness of those hidden dimensions. For it appears that a century after Lovecraft wrote about their horrors, we now think that there is possibly some truth to these ideas, but not quite in the way he proposed. For it turns out that yes, we may need to look to extra, higher dimensions for answers on the true nature of the cosmos, but from a lower viewpoint than we had originally thought. Our entire universe may be nothing more than a thin, 2-dimensional membrane. The answer to matter, gravity, and even space-time itself may lie in the reduction of dimensions. Einstein was not a slow starter. Documents show he was actually a child prodigy, excelling in physics. This was helped by being surrounded by electricity and magnetism in his youth. The Einstein Company, run by his father and uncle, manufactured electrical equipment. Encountering science at a young age was clearly a huge factor in his later development. His story is a reminder of just how powerful early curiosity can be, and nurturing that spark is exactly what KiwiCo aims to do. KiwiCo offers monthly, hands-on projects designed for every age and interest, from toddlers exploring the world for the first time to teens and even adults tackling advanced science, engineering, and art projects. My producer and his family had a great time with their crate from the Kiwi Crate subscription line, a monthly delivery for kids ages 6 to 9. They got to build their own planetarium, mix and match constellations, design star patterns, and even see how the Earth and Moon orbit the Sun. The kids loved the excitement of opening the box, and since the projects and elements are reusable, they've been able to explore them again and again. His family is already counting down the days until their next monthly delivery. So, if you'd like to spark that same excitement and inspire the little scientists and engineers in your life, use my code History of the Universe for 50% off your first monthly KiwiCo crate, or head to kiwico.com/History of the Universe. Possibly, Gilman ought not to have studied so hard. Non-Euclidean calculus and quantum physics are enough to stretch any brain, And when one mixes them with folklore and tries to trace a strange background of multidimensional reality, one can hardly expect to be wholly free from mental tension. Like Walter Gilman's exploration of his rented room, the journey to higher and lower dimensional answers is a strange one. And it starts in the most unlikely of places. Not in studies of the quantum nature of reality or the edge of the universe, but in an attempt to make more efficient steam engines. Death is nothing, but to live defeated and inglorious is to die daily. On the 15th of October 1815, Napoleon, once the Emperor of France and master of half of Europe, set foot onto his new domain, the tiny island of St. Helena, his second exile and final prison from where he would never return. It is said that during his final years on the rock, he insisted that the men who served him wear military clothing and the women evening gowns, his defeat at Waterloo months before hard to swallow. But it was final. Never again would he seize glory. Never again would he march in triumph. What he left behind was a fragile monarchy restored in France, a regime that did not take kindly to any friends and associates of the exiled emperor. And that included a young Sadi Carnot, an engineering officer of the French army. Born in 1796, Sadi was the son of Lazare Carnot, the brilliant mathematician and commander of the French Revolutionary Army, and one of the few who successfully navigated the turmoil of the rise of Napoleon. But Sadi would have no such luck. He maintained his position in the military, but was frequently passed over for promotion due to his family's connections to the exiled emperor. Eventually, he took a pay cut to secure what was essentially a sham position, but one that allowed him to spend time focusing on his intellectual curiosities. Curiosities that would change our entire understanding of how reality works. Believing that one of the causes of the French defeat was the inefficiencies of their engines, he sought to mathematically describe the perfect engine in an essay entitled Reflections on the Motive Power of Fire. Dying in 1832, however, his treatise never got the recognition it deserved in his lifetime, but it would later turn out that Carnot had unwittingly stumbled upon the building blocks of an entirely new kind of physics. Decades later, his book would catch the attention of Rudolf Clausius, a German physicist and mathematician. Something in Carnot's work fired his ingenious imagination, and in 1850, Clausius would state what would eventually become known as the second law of thermodynamics. And 15 years later, he would introduce the concept of entropy. He had no idea what he had unleashed upon the world. At its core, thermodynamics rests on three basic laws. The first law of thermodynamics is a version of conservation of energy. Energy cannot be created or destroyed, only transformed. The second law, first observed by Rudolf Clausius, states that entropy never decreases. This means, among many other things, that heat does not spontaneously move from a colder body to a warmer one. And the third and final law states that a system's entropy approaches a constant as it cools towards absolute zero, implying that it's impossible for any system to actually ever reach that point. And so central to the second and third laws was this new concept of entropy. Scientists going back to Newton believed that heat was some kind of particle that travelled from one object to another. But Clausius disagreed. While energy could not be created or destroyed, not all energy was usable. For example, when a piston is driving a motor, some of the energy is gainfully used to create movement, while some of the energy is lost to friction. When a fire is used to cook food, some of that energy is lost in light and excess heat. Therefore, Clausius reasoned, heat itself could be transformed, and we needed to keep track of the useful and useless kinds of heat. He dubbed this non-usable form of heat entropy. and so the three laws of thermodynamics obviously worked. They explained experiments and made powerful predictions, but in a sense they were created out of whole cloth. Where did they come from? What did they mean? When the first generation of pioneers like Carnot and Clausius passed, it would become the job of the second generation of explorers to understand the unfolding mathematical world that they created. And it was they who would find much deeper connections to the true nature of reality than they could ever have expected. It must be splendid to command millions of people in great national ventures, to lead 100,000 to victory in battle. But it seems to me greater still to discover fundamental truths in a very modest room with very modest means. Truths that will still be foundations of human knowledge when the memory of these battles is painstakingly preserved only in the archives of the historian. The exploration of this new science of thermodynamics would come to bear the greatest on Ludwig Boltzmann, an Austrian physicist born in 1844, more than a decade after the death of Carnot, and more than 20 years after Napoleon finally passed into the archives of history on St. Helena. For Boltzmann, a truly modern scientist, there was something deeper happening in the three laws, and he suspected it had something to do with the microscopic nature of materials. At the time, scientists around the world were just beginning to recognize and classify the elements of nature, like hydrogen and oxygen, and understand their properties. However, while most scientists had a sense that these elements were made of some fundamental unit, the atom, they hadn't yet proved it. Boltzmann's genius and bravery was to unite the burgeoning theory of the atom with the laws of thermodynamics. He envisioned gases and fluids as composed of countless tiny particles, and sought to understand how those particles interacted and behaved, hoping that those deeper interactions would naturally give rise to the large-scale thermodynamic properties that earlier scientists had recognized. With time, he would be proven right, and his revelations started with entropy. In 1877, Boltzmann created a new definition of entropy, this one based on the behaviors of countless microscopic particles within the whole, rather than a single uniform mass. His definition of entropy relied on counting the number of possible arrangements of tiny particles that can lead to the same observable large-scale property. And to help understand this, let's imagine you finally get around to cleaning your kitchen. You clean all the dishes and put them away in the cupboard. You take out the rubbish and recycling. You throw out the mouldy food from the fridge. You even clean the gunk out of the grout behind the sink. After hours of effort, you stand back to admire your handiwork. The kitchen is spotless. There is place for everything, and everything is in its place. Boltzmann would say that this is a state of very low entropy. You have the property you can measure, which is cleanliness, and for the kitchen to give you that property, there is one and only one way that everything can be arranged to make it clean. In Boltzmann's language, there is only one microstate of kitchen perfection that leads to the macrostate of cleanliness. But fast forward one day. You live your life, you make dinner, you clean up, you open the fridge for a midnight snack. In less than 24 hours, your kitchen is noticeably less clean. Boltzmann would say that your kitchen now has a higher entropy state. Your kitchen is slightly dirty. That is the observable macro state. And there are many, many ways to make your kitchen give you that observable property. Maybe there's a glass left in the sink. Maybe there's a crumb on the corner of the counter. Maybe your cup left a ring on the table. All it takes is for one little thing to be wrong, but there are so many options of what that one little thing could be. There are many more ways to be untidy than tidy. And this is how we arrive at our connection between entropy and disorder. Strictly, entropy is a measure of the number of microstates that lead to a specific observable thermodynamic state, like pressure and temperature. But also, the higher entropy a system has, the more microstates it has available, the more disorder it has. And this realization, this powerful connection between the possible arrangements of microscopic particles and one of the key concepts behind the laws of thermodynamics, birthed yet another new branch of physics known as statistical mechanics. We now understand that all of thermodynamics arises out of statistical mechanics, especially after the existence of atoms was demonstrably proven by Einstein in 1905. What we call temperature in a gas, for example, is the average kinetic energy of the particles of the system. Hotter temperatures mean greater kinetic energy, which translates as all the particles of air moving around with greater speeds. Thus, when we immerse our hands in a hot gas, all those particles slam into our skin, imparting their energy on us and transferring heat in the process. And so the key to statistical mechanics is that we don't have to know all the properties of all microscopic particles making up the system. We don't have to keep track of every single air molecule with its detailed position and momentum to arrive at an understanding of temperature. Instead, we only have to apply probabilities, hence the statistics in statistical mechanics, like counting microstates or computing averages. But, obviously, these 19th century explorers behind thermodynamics and statistical mechanics were not yet opening doors to new dimensions. Instead, they were developing a basic mathematical toolkit. Any object with heat could now be described by entropy, and entropy could be described in terms of microscopic motions. And in the coming decades, these tools would be used in the most unexpected places, the most unlikely objects to possibly have heat: black holes. And in the explorations of black hole thermodynamics, the first hints would emerge that something was very, very wrong with the universe. The dreams were wholly beyond the pale of sanity. He had been thinking too much about the vague regions which his formulae told him must lie beyond the 3 dimensions we know. As Lovecraft's story continues, Walter Gilman's dreams take him to a bizarre otherworld, a place he believes to be higher dimensional, full of abysses whose material and gravitational properties he could not even begin to explain. Lovecraft continues, the abysses were by no means vacant, being crowded with indescribably angled masses of alien-hued substance. Everything he saw was unspeakably menacing and horrible. Luckily, in our journey to the most extreme place in the universe, the logical endpoint of the study of thermodynamics, we will have a guide to help us. A guide with plenty of experience dealing with impossible demons. I look upon the world as a product of God. Jacob Bekenstein was a devoutly religious man, and yet the pioneering scientist did not see this as a barrier to his explorations of the extreme places of the universe, a tightrope that many physicists both before and after have walked. Indeed, Newton himself was a devout Christian, and more recently, Georges Lemaitre, father of the Big Bang, was a Catholic priest. Bekenstein delighted in unfolding the mysteries that God had left him, and saw studying the universe's inner workings as a form of worship. The more we learned about nature, he believed, the closer we came to knowing God. And yet the most famous of these explorations in the early 1970s would take him to the brink of something far more demonic than holy. Arguably, the most powerful source of ruin in the universe. Black holes. There is no greater monster than black holes, no grander destructive power. Nothing can survive an encounter with them, not planets, not stars, indeed sometimes even galaxies wilt in their presence. And of course, at first glance, they have nothing whatsoever to do with thermodynamics, statistical mechanics, or the extra or hidden dimensions of the universe. first found buried in the mathematics of Einstein's general theory of relativity, they are, in the words of Nobel Prize-winning physicist Subrahmanyan Chandrasekhar, the most perfect macroscopic objects there are in the universe. The only elements in their construction are our concepts of space and time. But despite this perfection, in many ways black holes created more headaches for scientists than they solved. In particular, in regards to two grand mysteries, both tied to their fundamental nature. First, the singularity, the point of infinite density at their centers as predicted by general relativity. Infinite densities cannot exist, and so their appearance was a clear sign that general relativity is not complete, that there is a more fundamental theory that has to be used to explain what is really going on. But unfortunately, singularities are forever inaccessible, because they are locked behind the one-way barrier of the black hole event horizon. Of course, you can travel beyond the event horizon if you dare, but like one of Lovecraft's unfortunate adventurers, you will never be able to reveal your findings to the outside universe. And it is these event horizons that present the other mystery. Black holes are the only places in the entire universe where you can enter but cannot leave, and so it left theorists questioning what this means. Are event horizons truly what they appear to be, roads of no return, or is there more to the story? These were the kinds of questions that drove Bekenstein. The singularities were a massive unsolved problem, but it seemed to him that the event horizons were just as mysterious, and they had the added bonus of actually being observable to the outside universe. And so by 1973, Bekenstein had discovered something uniquely strange about his pet demons. Despite their fearsome reputations, black holes are almost absurdly simple. From the outside, black holes only present three quantifiable properties: their mass, their electric charge, and their spin, or angular momentum. Regardless of what goes into them, whatever stars and gas and molecules, whatever planets and moons and comets, whatever man, woman, or child, all the information gets neatly tucked away from prying eyes behind the event horizon. All that we ever get to see is those three simple properties. Indeed, if you constructed two black holes from two very different sources, say one from a collection of stars and nebulae and the other from just information, for example, an incredibly long number, if those black holes had the same mass, charge, and spin, you would not be able to tell them apart. Bekenstein would go on to call this idea the no-hair theorem, in essence, the idea that black holes are bored of information. His mentor and advisor, John Wheeler, found the phrase delightful. Famous physicist Richard Feynman thought it obscene. But, despite Feynman's objections, the phrase stuck. The baldness of black holes led some theorists to suppose that black holes are regions of zero entropy, places of no information. But Bekenstein quickly realized that the opposite was true. Black holes could not be regions of zero entropy. It would mean that you could toss materials into black holes and destroy their information content, something completely forbidden in quantum mechanics. So Bekenstein realized that black holes must have an entropy associated with them. But how much? He proposed that black hole entropy is proportional to their surface areas, i.e., the size of the event horizon. The larger the black hole, the more surface area it had, the more entropy it contained in its volume. And it was this that led Bekenstein to make perhaps the most bizarre statement ever made about black holes, which, considering how bizarre black holes already are, was quite the achievement. He proposed what would become known as the second law of black hole thermodynamics, that black hole surface areas never shrink, that event horizons never get smaller. This was in analogy to the second law of thermodynamics, which states that entropy never shrinks in a closed system. And since Bekenstein guessed that black hole surface areas were proportional to their entropy, this new kind of second law popped right out as an immediate consequence. At the time, this was only a conjecture, an educated guess as to an intriguing property of these mysterious creatures. A bold guess, true, but still a guess. And then came Stephen Hawking. Hawking, unlike Bekenstein, was not a religious man. God is the name people give to the reason we are here, he said. But I think that the reason is the laws of physics, rather than someone with whom one can have a personal relationship. And yet there is no record of any clash, or this being the source of any tension between the two men. Hawking's qualms were solely with Bekenstein's physics, believing that whilst his work on black holes was intriguing and possibly profound, it was also riddled with errors. Hawking argued that black holes couldn't possibly have an entropy associated with them because they did not radiate. They didn't produce heat, and so we couldn't use familiar thermodynamic terms to describe them. And so Hawking set out to prove Bekenstein wrong, and in the course of his work found out that his rival was exactly right. By carefully following the evolution of the event horizon since the moment of a black hole's inception, Hawking discovered that the one-way boundary interacted in strange and unexpected ways with the surrounding spacetime. Through a quirk in quantum mechanics, particles could escape. Black holes were not black. They emitted, ever so slowly, a tiny amount of radiation. Hawking's result, published in 1974, was a bombshell. Long had physicists suspected that there was something more to black holes, but nobody had expected this. Black holes emitted radiation, later named Hawking radiation, with smaller black holes emitting more than larger ones. And that was not all. For the discovery of Hawking radiation, along with Bekenstein's original insights into the nature of black hole entropy, created perhaps the greatest paradox of modern science: the black hole information paradox. To begin with, Bekenstein's second law of black hole thermodynamics was ruled out. Black hole surface areas do not always grow. Instead, if left to their own devices, they shrink as Hawking radiation saps mass from the black hole. But Bekenstein had correctly discovered that black holes do have an entropy. If black holes didn't radiate, this wouldn't be a problem. Information is not destroyed, it's simply hidden from view for all eternity. But black holes do disappear, and eventually disappear entirely, and with them goes the information used to build them. Hawking had discovered that this black body radiation emitted by black holes did not and could not carry information with it. Hawking's calculations had showed it was essentially random. If you monitored the particles and photons emitted by a decaying black hole, you couldn't discern the internal contents of what made the black hole in the first place. And so Bekenstein's no-hair theorem stayed correct. Once a black hole consumes something, we lose access to the information of what that thing was. But then the black hole disappears. What now? If the information didn't escape through Hawking radiation, then where did it go? This was the heart of the black hole information paradox, the seeming ability for black holes to swallow and destroy information, something that went entirely against the hard laws of quantum mechanics. Information could never, ever be destroyed. And so, Bekenstein and Hawking couldn't both be right. Either the radiation must carry away information with it, meaning Hawking was wrong about its nature, or black holes are hairy after all, and Bekenstein was incorrect. And it is this paradox that has proved so seductive to physicists ever since those fateful years in the early 1970s, and it is this paradox that has teased bizarre clues about our dimensional reality. Our story began with Carnot and his desire to make steam engines more efficient. Then Clausius refined his work, creating the laws of thermodynamics and inventing the concept of entropy. A half-century later, Boltzmann would discover that thermodynamics arose from more fundamental physics. And now, we have black holes, which seem to show properties similar to thermodynamics, with radiation and entropy. So if thermodynamics arises from some more fundamental physics, then perhaps black holes do as well. But what does this connection tell us about the ultimate nature of reality? Well, the key to all of these mysteries may not lie deep in their hearts, but right on their surfaces. For in parallel with the work of Bekenstein and Hawking would come another line of research, not one devoted to black holes at all, or even astrophysics, but in the studies of light and lasers. And in those studies, we would find that in some special cases, the 3 dimensions of our universe were not always necessary, and sometimes only 2 would suffice. What made the students shake their heads was his sober theory that a man might, given mathematical knowledge admittedly beyond all likelihood of human acquirement, step deliberately from the Earth to any other celestial body which might lie at one of an infinity of specific points in the cosmic pattern. Any being from any part of 3-dimensional space could probably survive in the 4th dimension. Walter Gilman's dreams start to take him over and bring him to seemingly otherworldly dimensions. Quickly, he begins to lose his grip on reality. And so, just as Gilman seems able to cross from our 3-dimensional reality to higher dimensional ones and reap the consequences, is it possible for us to do so, even if only through the window of modern theoretical physics? And if we can, if we are able to catch a glimpse of these extra-dimensional worlds, what would it mean for our own? To start to understand this, and the bizarre reality it may hint at, we have to go back to the early 20th century and a young boy on the front lines. Born in 1900 in Budapest, Hungary, as a teen, Denis Gabor served in an artillery corps with the Austro-Hungarian army in that kingdom's struggles against Italy in World War I. Between the wars, Gabor studied in Germany, becoming readily adept at working with electronics. But in the early 1930s, the incoming regime put him in danger. He was of Jewish heritage, and despite his service in World War I, this meant little to the Nazis, and so in 1933 he fled, taking up an invitation to work in Britain. Yet despite this upheaval, he never gave up on his fascination with electrons, light and lasers, and it would be in Britain that Gabor would make a remarkable discovery, a technique that he dubbed holography. When you take a photograph, most of the information is destroyed. For example, imagine taking in a beautiful mountain vista. You can stand on a high ledge to get a better vantage point. You can walk around to see the other side. You have the freedom to explore it fully in all its 3-dimensional glory. But once you take out your phone and snap a picture, that freedom is lost. You are locked into one perspective forever. If you print the photograph and put it on your wall, you can still walk around and get different perspectives of the photograph, but not the scene itself. If you walk around behind it, all you'll see is the back of the frame, not the other side of the mountain. Photography inherently destroys information, but Gabor found a clever way around this limitation. He discovered that by cleverly interfering light from multiple sources, he could fully encode 3-dimensional information onto a 2-dimensional film, essentially recording how light bounces off an object. This meant that when light was shone the same way on the object, the hologram would recreate the original light pattern. and so when projected properly, he could recreate the original scene in all its three-dimensional glory. Indeed, with a true holographic projection, you can take different vantage points, walk around the object and more, just as you could the original object. While revolutionary, Garbor's invention in 1947 didn't reach the mainstream. Indeed, it wasn't until 1971 that he was awarded the Nobel Prize for his work, and even after that, the general public was only aware of holography as a sci-fi novelty, such as in scenes like Princess Leia's plea for help in Star Wars. Yet while the general public only got to experience holography through cheap and artificial imitations, for example, the holographic stickers or cards you might encounter that are not really holograms, just laminated printing, the physics community quickly noticed the deeper implications. For in some special cases, if arranged just right, it seemed that a three-dimensional world could be reduced to a mere 2 dimensions, all without destroying any information at all. And there was one man who was central to this revelation, a man also caught up in the chaos of World War II. I could smell the war coming along, and it seemed to me I would be safer working full-time for the war effort, safer against the draft. But not only that, I thought I'd probably contribute a hell of a lot more. Claude Shannon started working for Bell Labs in 1941, and would certainly go on to contribute a lot more in his time there than he would have done on the front lines. Constantly thinking about mathematics, he would write equations on napkins during meals. Indeed, one colleague would go on to refer to him as intellectually insufferable, so gifted and impatient that he towered over others he worked with. During the war, he worked on cryptography and met several times with Alan Turing, but it would be after Berlin had fallen that his greatest work would be revealed to the world, for in 1948, he would write a groundbreaking paper on the nature of communication and cryptography. In that paper, he devised a way to measure the amount of information needed to describe the possible different states of an unknown thing. Shannon found, to his surprise, that the formula for this quantity clearly resembled Boltzmann's formula for the entropy of a gas. So he used the same term to describe what he found, and in the process, entropy became almost synonymous with information. Shannon's work was a landmark, not just in information theory and computer science, but it quickly gained momentum in physics circles as well. What matters to physicists is the state of a system, a list of all its properties, like the position and momentum of all the particles in a certain volume, that can be used to exactly predict all its future behaviors. Sometimes this list is very simple, and we can keep track of all the accounting by hand. For example, if we are tracking the trajectory of a projectile, we only need to record a few variables, the position and momentum of the object, to find out where it will land. However, sometimes this list is exceedingly long and complex, and we have to turn to emergent properties, with tools like statistical mechanics to get the job done. An example of this is anything to do with gases. It would be fruitless to try to record the exact motion of every single molecule in a chamber, the number of which can easily exceed the total number of stars in the observable universe. So instead, we use summaries like temperature and pressure to get an average sense of the particle's overall behavior. But the key is that information lies at the heart of the predictive power of physics. Once you know all the information about a system, and you know the laws of physics, then in principle, you know what the system will be like in the future. Of course, quantum mechanics altered this framework slightly due to the fundamental uncertainty found in microscopic systems. Instead of firm predictions, there are instead loose probabilities. But other than that, the game was still the same. Keep track of the information, the general probabilities, predict the future. And so it was no accident that Shannon chose the word entropy for this measure of information. When it comes to thermodynamic systems, there is a clear mathematical link between the entropy of the system and the amount of information needed to describe it. Indeed, the formulas used in Boltzmann's and Shannon's calculations, despite coming from completely different directions in entirely different fields of study, were eerily similar. The apparently close connection between Shannon's entropy and Boltzmann's of the relationship between thermodynamics and information went as far as to lead John Wheeler, Jacob Bekenstein's mentor and a giant in the theoretical physics community, to propose it from bit, that perhaps information, not matter and energy, formed the central core of reality. But even if we don't go to those lengths, this similarity between the different kinds of entropy means that any time we can find in nature a process that follows the laws of thermodynamics, then we have a clear measure of the information content of that system, quantum or not. And as Jacob Bekenstein discovered and Stephen Hawking confirmed, black holes seem to behave as thermodynamic systems. Indeed, it was Bekenstein's investigation into the nature of information as it fell into a black hole that led him to argue that they had an entropy, and years later he would discover another remarkable property of black holes. Not only do they have an entropy, but there is no other place in the universe with more entropy than their surfaces. And so from Shannon's work, this meant Bekenstein understood something else. There is nowhere in the universe that contains more information than the surface of a black hole. To get a handle on how detailed the accounting needed to be for this discovery, Bekenstein employed something called Planck units. Invented by the father of quantum physics himself, Max Planck, these units describe the scale at which quantum mechanics takes over entirely. To arrive at these units, Planck had to combine various universal constants: the speed of light, the gravitational constant, the Planck constant, and so on. He created units for time, mass, and most importantly for our story, size. The Planck length is the square root of Planck's constant times the gravitational constant divided by the speed of light cubed, and is roughly equal to 1.6 times 10 to the power of minus 35 meters. Planck calculated that this represents the smallest possible distance, the scale where quantum mechanics meets gravity, and our normal conceptions of space-time break down into the quantum foam. And it was these Planck lengths that Bekenstein used in 1981 to explore how much quantum information a given volume contained. He expressed this in terms of a limit. There was a certain maximum amount of entropy in any volume, and it turned out that black holes had exactly the maximum amount of entropy possible. The entropy contained inside a black hole, or equivalently, the information contained inside a black hole, was exactly proportional to its surface area. And perhaps most surprisingly of all, adding one bit of information to a black hole seemed to increase its surface area by exactly one Planck area, the Planck length squared. Black holes contained the most amount of entropy possible in a given volume, and when we added information to them, their surfaces, not their volumes, grew in perfect proportionality. And it wasn't just black holes. It turned out that the total amount of entropy in any volume of space grows as the surface area of that volume. It's just that black holes contain the maximum possible amount. It seemed that entropy, and therefore information, cared more about surface areas than volumes. In other words, entropy and information related more closely to 2 dimensions, not 3. This was Garbor's theory of holography made manifest in a truly bizarre direction. No longer mere reconstructions of images with encodings of light, but the very basic and most fundamental summation of information and entropy, encoded in the fabric of space-time itself. And these remarkable findings have led to a bold and possibly foolish proposition. Perhaps black holes are holograms. Perhaps black holes don't exist in more dimensions, but fewer than we think. Maybe black holes are only surfaces, only beings of 2 dimensions, not even a thin surface enclosing a substantial volume, but consisting of nothing but the surface alone. And this line of thinking has even brought about some possible solutions to the black hole information paradox. If black holes really are holograms and really are only 2-dimensional, then nothing truly falls in. There is no in. They have no interior. Any material stays on the boundary, the event horizon, because that's all there is. When the black hole emits Hawking radiation, it would do so from this same surface. In this view, both Bekenstein and Hawking were slightly wrong. Black holes needed to have hair. They would need some information preserved on their outward surfaces, and Hawking radiation couldn't be precisely blackbody. It had to carry away the information in some subtle, entangled way. And so, the portrait we were beginning to uncover was that black holes were something more than mere astrophysical entities like stars or planets. They may be some sort of strange, emergent phenomenon, something that operates at a deeper quantum level but manifests itself in our universe as simple 3-dimensional objects. But, of course, that was not the end. Because black holes are objects of pure, uncontrolled gravity. They are geometric punctures in the fabric of space-time itself. This means that what black holes teach us about the universe applies not just to themselves, but to the very fabric of the cosmos. And so what would we find as we continued exploring this path? Only by plunging forward would we know. It would be barbarous to do more than suggest what had killed Gilman. There had been virtually a tunnel through his body. Something had eaten his heart out. In the end, Walter Gilman's quest kills him. After encountering all manner of strange creatures on his travels to extra dimensions, he eventually meets a grisly demise. Walter Gilman knew that he was exploring dangerous realms, but he simply could not resist the temptation. His dreams took him to lands outside our universe, a land that his mind lacked the capacity to comprehend. Indeed, when you follow the laws of physics to the edges of our understanding, the implications quickly become overwhelming. And so perhaps that is why Juan Maldacena prefers clean, sparse offices. A simple desk, a chair, and a chalkboard, perhaps a window to let in some light or a gentle breeze, but no posters, no executive toys, no scattered papers and letters, just privacy from the outside world and a place to free himself from distractions. A room where he can let his mind wander and his imagination take charge. For me, any quiet place with no visual or auditory distractions would work. I think that curiosity and the intellectual challenge are important motivations, the desire to explore the unknown and to go beyond where others have gone. Born in Argentina, Maldacena was a wonder kid, making his way to Harvard University and then on to Princeton's renowned Institute for Advanced Study at the tender age of 33. A section of campus free from students, with a list of past professors, the envy of any university in the world. From its earliest days, when Einstein and Oppenheimer walked its gardens, to the modern-day giants of Ed Witten and Andre Geim, the Institute had long been a center of bleeding-edge theoretical physics. And it was pretty clear why Maldacena had been chosen. In 1997, Maldacena's first major insight had rocked the worlds of both physics and mathematics. Indeed, since then, this paper has been cited over 20,000 times, making it amongst the most top-cited physics papers of all time. Maldacena discovered not just a key, but a doorway into a totally new realm, one in which not just black holes, but the entire universe, everything we know and love, everything we can see and touch, was nothing but a dim projection of a two-dimensional reality. Although the paper had not appeared in a vacuum. Physicists had not been quiet between the earlier revelations of Bekenstein, that black holes have the maximum amount of entropy possible and that their surface areas grow in proportion to the amount of information contained within them, and Maldacena's new insight. In fact, in the early 1990s, Gerard 't Hooft, a Dutch theorist and eventual winner of the Nobel Prize, had proposed that the entire universe might be a hologram, and in 1995, Leonard Susskind had taken these ideas and literally written a paper titled The World as a Hologram. The thinking behind this leap of imagination was that black holes teach us about more than just black holes. They are objects of pure gravity, and they offer us the best testbed we have for probing at the fundamental nature of that force. Einstein taught us, through relativity, that gravity is an expression of the warping and bending of space-time. Matter and energy bend space-time around them, and that bending dictates how other objects move. Everything we understand about gravity, from the projectile motion of a tossed ball to the evolution of galaxies and beyond, is really a story of the deformations in space-time and our response to it. But a change in our understanding of gravity through a quantized lens has the power to alter this picture, and a new picture of gravity could lead to a new picture of space and time. And space and time are more than mere mathematical abstractions. In some sense, space and time are the universe, in a much more fundamental and essential way than the matter and energy that lives inside it. And so black holes teach us about the inner workings of gravity, and the inner workings of gravity teach us about space and time, which in turn teaches us about how the universe is constructed at its most basic level. So, what exactly were the black holes teaching us? Well, to begin with, they were telling us gravity seems to care more about surfaces than volumes, at least when it comes to information. But it wasn't a physical theory. And this is where Maldacena came in. The most popular proposal amongst professional physicists for a quantum theory of gravity is string theory. The key picture behind string theory is that matter is not fundamentally made of point-like particles. Instead, the basic constituents of materials are tiny strings, each one roughly the size of the Planck length. These strings vibrate, and the different fundamental modes give rise to the plethora of particles, like different notes plucked on a guitar string. And the possible vibrations of the strings also include a particle with the expected properties of the quantum force carrier of the graviton, which of course immediately made string theory an alluring picture of reality. There are, however, two major issues with string theory. One is that in order to accommodate all the varieties of known particles, the strings can't just vibrate in 3 dimensions. Instead, they require more freedom of movement. The earliest versions of string theory required the existence of 26 dimensions, with more modern versions needing only 10 or 11. And the second problem with string theory is that nobody has been able to turn it into a working theory of physics. After a half-century of effort and countless attempts, nobody knows how the extra dimensions curl up on themselves, how the shapes of those curled-up dimensions affect the vibrations of the strings, how the vibrations manifest as particles, and how all this connects to our understanding of space-time. These all remain unsolved problems to the present day. But in 1997, Maldacena found a clue, and that clue was in the holographic nature of black holes. Inspired by this intriguing connection between the information contained within black holes and their surface areas, Maldacena started playing around with similar holographic concepts in string theory. and what he discovered was something known as the ADS-CFT correspondence. The ADS stands for anti-de Sitter space. This is a particular kind of pretend model universe that is entirely empty of matter but contains a negative cosmological constant. The CFT stands for conformal field theory, a special kind of quantum field theory. Maldacena discovered that when he examined the special case of an anti-de Sitter universe existing in 5 dimensions, that instead of trying to solve string theory directly within its volume, if he instead projected onto its 4-dimensional surface, the equations transformed into the kind that could be solved through conformal theories. In other words, maybe string theory is so difficult for us because we're not looking at the universe the way it really is. If the universe is a hologram, as suggested by Bekenstein's results for black holes, then perhaps we shouldn't care about the 3-dimensional volume and instead focus on its 2-dimensional surface. There, the seemingly impossible to solve equations of string theory might transform into difficult, but at least solvable, quantum calculations. Nearly 20 years after its publication, the ADS-CFT correspondence remains a cornerstone of holographic principles in action. But the story isn't over yet. The correspondence, while seemingly powerful, has not been mathematically proven, and while it works in the toy universe constructed by Maldacena, nobody knows if it applies to the real, physical cosmos that we inhabit. Despite these limitations, physicists have soldiered on. Indeed, almost all work in modern string theory is focused not on the theory itself, but on the implications and possible extensions to the ADS-CFT correspondence. That's how seductive this idea is. The first time someone was able to make a convincing link between the physics of the unknown and the physics of the known. The first time someone was able to build a bridge between string theory and quantum theory. And so, Carnot, Clausius, Boltzmann, Shannon, Gabor, Bekenstein, Maldacena. A chain of thinking leading us to an unlikely conclusion that our universe may be a hologram. We now stand upon the very precipice of knowledge. Behind us, centuries of exploration into hidden realms. We do not know if our universe is a hologram or if information is the fundamental unit of reality. We do not know the connections, if any, between gravity and thermodynamics. But if these ideas are real, if the universe is a hologram, then it has profound implications for how we view the cosmos. But, unfortunately for the Victorians, these insights do not lead to a new 4th dimension full of spirituality and mysticism. Instead, these insights reduce the universe, insisting that it is truly 2-dimensional, and that our 3-dimensional experience is an illusion. The real information and the real physics stays on the boundary. That is where everything, you, me, and all the stars and galaxies of the universe, would live. Like the creatures of Lovecraftian lore, we would not directly perceive the full complexities of the quantum information in this hidden 2-dimensional membrane. It would be too far removed from our conscious experience of the world. We would be too constrained by the genetic heritage that forms the biological basis for our brains. Although, many disagree. Despite the alluring nature of holographic theory, there has still been nothing proven or conclusively demonstrated despite decades of work. We still haven't cracked string theory, and we still haven't proven the ADS-CFT correspondence either. Black holes are as mysterious as ever. Indeed, string theory itself is on shaky ground after the Large Hadron Collider failed to find evidence for supersymmetry, a key underlying component of the theory. And without string theory, the entire holographic program may be at risk. Perhaps steam engines are just steam engines, and black holes only coincidentally look like them, Or perhaps we're just misunderstanding entropy and the nature of quantum information. Perhaps we've been on the wrong path this entire time. And so, is this a warning? Is the universe trying to tell us something? What will we find if we keep exploring? Will we find more hints, more tidbits, more strange and unexpected connections? Or will we twist ourselves in knots of our own making, our feeble human minds unable to grasp concepts outside of our mental reach? There's only one way to find out. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.